Mathematicians have a habit of asking strange questions. One of the strangest is this: is there a function so lazy that no matter how many times you differentiate it, it simply refuses to change? Standard functions change their physical shape when we differentiate them. X squared becomes 2x, sine of x becomes cosine. But one specific function looks at the process of differentiation and stays exactly the same. To find this function, we have to look at the limit of growth. Imagine you put $1 in a bank that offers 100% interest per year. If it compounds once, you end the year with $2. If the bank compounds that interest more frequently, the total grows. Compounding twice a year results in 2.25. 4 times gets you to 2.441. And compounding every month leads to 2.613. If we compound the interest continuously, every second, every millisecond, without ever stopping, the number stops climbing wildly. It stabilizes and settles at exactly 2.718. This is the constant E. This value emerged directly from the logic of continuous growth. It wasn't invented by a person or chosen as a convenient approximation. It is a mathematical property of systems that grow smoothly. Because E is the numerical ceiling for continuous growth, the function e to the x serves as the mathematical description for any value that increases at a constant, uninterrupted rate. To see why this function resists differentiation, we need to look at its geometry. Differentiating a curve simply means finding its slope at any given point. Here is the curve of e to the x. We can test its unique property by measuring the slope at different coordinates. At x equals 0, the value of the function is 1. When we measure the slope at that same point, it is also exactly 1. If we move to x equals 1, the value is e, roughly 2.718. The slope of the curve at this point is also 2.718. At x equals 2, the value is 7.389. Again, the slope is identical to the value, 7.389. This isn't a coincidence for specific points. At every single coordinate along this curve, the slope is equal to the value of the function itself. Because the slope is the value, differentiating the function produces the exact same function we started with. You can differentiate it 100 times and it will never change. E to the x is lazy because it represents self-proportional growth. It describes any system where the rate of change is exactly equal to the amount already present. We can move from geometry to algebra to see this property from another angle. To do this, we use the Taylor series to express e to the x as an infinite polynomial. The series looks like this: 1 plus x squared over 2 factorial plus x cubed over 3 factorial, continuing on forever. Pause the video for a moment. Apply the basic power rule for derivatives to every term in the sequence. Calculate what happens to the 1, the x, and the fractions. Differentiating term by term, 1 becomes 0, x becomes 1, x squared becomes 2x over 2 factorial. Simplified, numerators cancel with factorials. Every piece differentiates into the previous piece. The polynomial regenerates perfectly, proving the derivative is e to the x. Doing the calculus yourself reveals the infinite recursion that is built into the very architecture of the function. This recursive property is why e to the x appears in almost every branch of science. It models radioactive decay, the cooling of a heated object, and the growth of populations. This single constant connects the foundational units of geometry, algebra, and complex numbers. We see this in Euler's formula: e to the power of I times pi plus 1 equals 0. It is the link between the most important constants in mathematics. E to the x remains unchanged by differentiation because it is the mathematical definition of a process where the present state completely dictates the speed of future change. It is the core language of any system that grows into itself.